Bismillahirrahmanirrahim. Assalamu alaikum, ladies and gentlemen. I am here once again to give you some of the brief explanation of the multicollinearity. If you remember, in the previous lecture we started about talking about the multicollinearity, and now this lecture I would start with the previous summary. So what we learned in the previous lecture, simply we saw what is the multicollinearity. I think I discussed in detail, but it is necessary as we will continue this discussion of multicollinearity from this lecture. So I want to connect the previous discussion with this discussion. So what I was saying, that what is the multicollinearity? Simply if the independent variable, the regressors, are exactly linked with each other, this is called the multicollinearity, or you can say perfect multicollinearity. What are the sources from where the multicollinearity enters into the data of a researcher? There are many sources from it is there. So you will have to plug each and every loophole so that you avoid the minimum entrance and appearance of multicollinearity in your data. So what was the first source? The first source is that the range of variation of your independent variable is limited. What this means, that your variable can change, but the limit is very small. They can't change extraordinarily or in a wide range. The other source of multicollinearity is that it comes from the natural physical constraint into the population, as I explained with the example of the electricity and the income and the house size. That the people who have higher income, definitely most of the time they have larger houses. The other was that the multicollinearity may arise from the situation that there is a polynomial term in your data. One side, it is already the range is lower and you are introducing the polynomial term into the data. Among others, these were some of the you can say the sources of multicollinearity. Now we are much worried about the consequences. When we talked about its repercussions, we talked about that theoretically there is no problem. Our parameters are below best linear unbiased estimators, but when we do practically, then we face a number of problems. And what was the major problem? That although if there is no exact multicollinearity, now we are talking about the higher collinearity, because if there is perfect collinearity, you will be unable to determine your coefficients of regression. But now we are saying that the multicollinearity is greater than 80% and less than 100%. So in this case, theoretically no problem. Again, I will be repeating that the beta remains below, but at the same time when you are doing practically, now the problem rises. What the problem is? You come up with the larger values of the variance of the betas. So as the variance of beta increases, the precision measurement becomes, you can say, the loser. So what we say, that as the standard error becomes higher, the class and the confidence interval automatically expands, because it is based on this standard error. So as your acceptance region increases, now the probability is that you are the probability increases that you are unable to reject the null hypothesis. And what is your null hypothesis? Most of the time your null hypothesis that your parameter is insignificant or is equal to 0, or it is not statistically different from 0. The discussion from where there was a break of the lectures, the discussion was the detection, that how to detect that there is multicollinearity in the data, because our ultimate purpose is to make a remedy of if there is multicollinearity in the data, because we may avoid the problem of the increasing the probability of the rejection, the acceptance region. So we talked about only two methods. The first is the simple guess is that as you see that the R square is very high, but at the other side you see that the T statistics are insignificant, you should immediately make suspicion that you should suspect that there is some problem of multicollinearity. The other we talked about this is that you see the pairwise correlation among the regressor. If you see that the pairwise correlation is very high, then you can guess that there is a problem of multicollinearity. And where we stopped, we were talking about the third method, that how to detect multicollinearity. So I would like to just give a further example of this. So what this means, auxiliary regression, what this means, for example, now I am writing in, this is y is now in this form, I am writing x1, x2, x3 and xi. So what this means, I am bit quick because I have explained further. Now what I am saying, I will run the auxiliary regression. Now I will be ignoring y for the time moment. I will run x1 on all the other x's. Similarly, I will run the x2 on all the x's. Similarly, x3, and this will lead to xn. xn, or you can say the xi. So what does this mean? Against each regression you will be finding the values of fi. f1 you can say, this is f2 and this is fi. So what is this? There is a formula how to find these values. What is the formula? Every time you will be needed the r square, this will be r square 1, r square 2 and this will come to r square n. So these have the information and you can immediately calculate this from that. This is the formula for this, this is, and this is, k is the number of parameters to be estimated in your auxiliary regression, and this is the situation. So what this is now, as you will calculate the f, and if you see your calculated value of s, c means calculated is greater than the f tabulated, it means there is multicollinearity in your data. What was the in this base, why we reject, we say that our null hypothesis was that there is no multicollinearity in the data. So when this will be becoming greater than this, we will reject our null hypothesis, that is the H0. So when it is the H0 we will reject, we will say that there is it is rejected, so there is multicollinearity in the data. So this is the auxiliary mean, the helping and many other regression that we are estimating. The rules of thumbs to detect the multicollinearity continues, and there is the fourth method that is called the Eigenvalues and conditional index. So we will be making conditional index on the basis of the eigenvalues. What are the eigenvalues? These are reported by many of the softwares, and I think these are not reported by the eViews, but the software like SAS, these are it reports the values of the eigenvalues. So what this means, if we have the eigenvalues, we can make some formula and we can test whether there is multicollinearity or no multicollinearity. For example, from these eigenvalues, we can derive what is known the condition number k. The formula for condition number k, we will be talking about this. How this can be derived? The k is equal to maximum eigenvalue divided by the minimum eigenvalue. There will be it will be reporting the maximum and the minimum eigenvalue. So when you have the values of these two eigenvalues, you can calculate the k index, the k number. So k number is, I will be giving some example, and from this k number, if you take the square root of this k condition number, it becomes conditional index. Now there is not a big difference. The difference is only that the conditional index takes the under root of the k condition number, and otherwise there is no difference. So what is the rule of thumb? We will be calculating it by supposing sum of the values. So what is the rule of thumb? Rule of thumb is that if your k, now I am talking about that we have calculated this k. If the value of the k is between 100 and 1000, 100 and 1000, then what is, there is moderate or moderate to strong correlation. Moderate correlation strong, as you are very near to 100, then there is moderate multicollinearity, and if you are, when you are very near to 1000, there is very strong collinearity. And if your statistics, or you can say if the value of k exceeds 1000, there is severe multicollinearity. So it means indirectly it is also a confidence interval, and we say there is a lower bound and the upper bound. And if we are concentrating it on the k, that is the condition number, then we will be saying that this interval is between 100 and 1000. And the more you are near towards 100, there is moderate multicollinearity. But as you are going very near towards the 1000, there is strong, or you can say the severe strong multicollinearity. And if your calculated value goes beyond this, then there is also a very, very strong, or even you can say the severe multicollinearity. Now come to this, now you will be working intuitively, as you can see that this confidence interval, that this is the condition index, is now a simply square root of the k index. So what is this? Now just taking the under root of 100, now our interval comes 10, and this is the 30, although it is the under root of 900, we say that when we are looking at the condition index, our interval becomes this way. So what is this? If our calculated CI, now this conditional index, this was, if this is in this area from its values between 10 to 10, then there is multicollinearity starting from moderate to strong. And as you are very near to 30, there is strong multicollinearity. And if you are very near to 10, there is low multicollinearity. But if the value of the conditional index, it increases greater than, it becomes goes beyond this level, then there is higher and severe multicollinearity. We would be explaining it example. For example, suppose here, what you suppose the maximum eigenvalue, suppose this is, we suppose that this is equal to, you can say this is 2, and we say that the minimum eigenvalue is equal to 0.001. Now we want to see that whether there is multicollinearity. Definitely there is multicollinearity. We have to see it, because in the previous discussion I explained that we are not concerned about whether the multicollinearity is present or not. It is present there, but we are worried about its degree. We are just testing that whether it is strong, it is moderate, or it is severe. So now we have to calculate. If I go for the k index, k number, its formula is maximum eigenvalue divided by minimum eigenvalue. So this is the formula of this index. So if you see that, look at this, this is 2, that is the maximum eigenvalue, and I divide it by 0.001. So it will become equal to 2000 over 1, and ultimately it is 2000. So now look at this, the range of the k is between 100 to 1000. Now our 2000 is outside this range. So what we will be saying that there is severe multicollinearity. That there is, and we should be worried about this because there is very, very severe multicollinearity. Now if I go from K to this K to, I go to conditional index. Conditional index formula is nothing but it is the maximum eigenvalue divided by minimum eigenvalue, and this is the under root, and it is simply the under root of K. So what this means, I am just interested to see that this is the under root of this one. So if I take the under root of this, it will be, I am thinking about that it should be round about 40, 43 or 45, whatsoever you can calculate it. So now in the case of confidence interval, the interval is between 10 to 30. Again, whether you use the confidence, you use the conditional index or you use the K number, the situation never changes because only there is no difference between the formula. As you take the square root, you also take the square root of the range also. So now in this case our range is from 10 to 43 and this is falling outside the range. So we will say that there is severe multicollinearity, and that is a big problem. And fortunately, if I can change just for a view, that if I say that this is the maximum eigenvalue and this is the minimum eigenvalue. So in this situation, well, what it will be, it will become 200, and now you can see that this is in both the categories. If I take this K, it is within this limit. So there is moderate, I will say that there is moderate multicollinearity. And on the other hand, if this is the situation, I take the under root of this, it is almost, I can say this is 14, almost 14 to 15 some point. So if this is the, for example, I suppose that this is the 14th, now I have no calculator and I cannot precisely make the under root of 200. I can just guess. If there is some error, you are now you are using the quantitative techniques, and you know there is always a margin of error there. So for example, it is 14 and I want to test it by the conditional index. You will see that this value is falling here, and again there is moderate multicollinearity. So what is the crux of this discussion? That we have another formula for this, and that is called the K number, and the other is the conditional index. Both are the similar things, only with only the difference is that in one case we are taking the under root, and the other case we are not applying this. So what this means, we have the now range. Immediately we will calculate. You will be getting the values of this eigenvalues from the statistical software. There will be it will be reporting there. If there is no report, then it is difficult to calculate this one. This was the fourth method to how to detect that whether there is multicollinearity or not. The fifth method is the rules to detect multicollinearity. That is the tolerance and variance inflating factor, VIF. This is variance inflating factor. So you immediately comes that there is something that is increasing the variance. So variance inflating factor, and we use it as indicator of multicollinearity. So VIF now, the variance inflating factor, is now an indicator of multicollinearity. The larger the value of VIF, there is the more troublesome, or you can say the collinearity among the variables. So what is this? the variance inflating factor means that this is a factor that increases the variance. So as it has a greater value, then we will be saying that there is multicollinearity in the data, and its formula is very simple. This is 1 over 1 minus r square 2 3. Now this is the r is here. Now the coefficient correlation, and this is coefficient correlation 2 3 mean between x2 and x3, and I am assuming that there are 3 variables in the regression, and these are to the regressor. So now look at the formula. If I would like to write it again, 1 minus, if the correlation between x2 and x3 is higher, and you know it go up to maximum, the higher correlation is, this is VIF. The higher correlation here means that the denominator become lower and lower. The denominator become lower and lower, and this whole term will become bigger and bigger. So what this means, if there are higher correlation between the variable, then the VIF factor, that is the variance inflating factor, it becomes higher. And as we get the higher value of the VIF, we say that there is a problem of multicollinearity. So rule of thumb, what is this? How to reject it? If the variance inflating factor exceeds 10, if it is up to 10 or below 10, then there is not a problem of multicollinearity. And when it will exceed the 10, when the r square is 0.90. Look at here. For this 1 over, I say that the r square, that is the coefficient of determination, this is r square is, for example, this is the coefficient of correlation, r is the coefficient of correlation, and I say that it is 95% or 0.95. So this will become 1 minus 0.95. So this will become 1 over 1.1, this will become 0.05. And if I multiply it, solve this, it will become 1 over 5 multiplied by 100. So it will become 20. So as the r square, here the capital R square means that as the coefficient of determination increases the 90%, then the VIF, that is the variance inflating factor, it goes in the red zone. And what is the red zone? Red zone starts for VIF at 10. So as the value of the VIF or the variance inflating factor, it goes beyond 10, then there is a, you can say, then there is a troublesome problem of multicollinearity. I think you have got the idea. And the other is the tolerance factor. This is the tolerance factor. And if you see that this formula has been derived from 1 over VIF, from the same VIF. So if you look at this, it is the similar story behind this as was in the previous slide between you can say between the K and CI. This is the similar story between tolerance factor and the variance inflating factor. So what is this? The formula between this is that the tolerance is equal to 1 over VIF, variance inflating. Now you can see that there is a negative relationship between this. As the value of the variance inflating factor increases, the tolerance level decreases. So what this means, again the same thing, that when there is higher value of VIF, there is a small value of tolerance. As VIF goes to infinity, tolerance goes to 0. tolerance factor goes to 0. So what does this means? In the previous slide we said if we have higher value of VIF, as we said here somewhere, that if it exceeds 10, if VIF is greater than 10, its value is greater than 10, then we say that there is severe multicollinearity. So here what is happening here? The same situation here. So as the value of this tolerance goes near towards 0, then there is severe multicollinearity. So the more the tolerance is going towards 0, there is more multicollinearity, and as it is going beyond this 0, there is moderate or less multicollinearity. So this was the fifth method, that was the tolerance and the variance inflating factor. Almost these are the same things as there in the previous slide. There was the K and CI. You may be given some of the values and you may have to calculate this tolerance, or you can say, you should say that, guess that whether there is multicollinearity or not. Now we have just seen that how to detect. Now I suppose that you have detected that there is the problem of multicollinearity. Now how to remove this problem, because you are only a good doctor when after diagnosing the disease you are in a position to suggest a medicine that ultimately leads to the benefit of the patient, and patient get rid of that disease. So what can be done if multicollinearity is serious? Keep in mind that if the multicollinearity is less than 80%, it is not a bigger problem, because you can't say that there is no multicollinearity. Multicollinearity is always in your data, but you should be worried about whether it is moderate, severe, or you can say the strong. So we have two choices to deal with the multicollinearity. The first is very interesting. Do nothing. This is very, very interesting, that one school of thought says that if there is multicollinearity in the data, do nothing. The other says no, rather than putting just your finger cross, you should do something, and there are some rules of thumbs. We will be talking about this, that how we can reduce the multicollinearity if there is higher multicollinearity. So first we will be touching the interesting school of thought that says do nothing. This school of thought is led by Blanchard. He said that when the students, as you are the beginner, when you will run the regression and you will estimate your coefficients, regression coefficient by OLS, according to the Blanchard, the first problem that usually is faced by the student, that is the multicollinearity. And when you see the multicollinearity, what happens to the students? They blame the OLS, ordinary least square. They do not think that the multicollinearity has come from some other source. They just criticize the OLS. They think that their method was wrong, method of estimating was wrong. So what is there? There are alternative available to ordinary least square. So what they will be doing, they will changing their methodology. For example, I suppose they are estimating it by maximum likelihood. So rather than criticizing OLS, they should understand that according to the Blanchard, this is God will. According to the Blanchard, that is a big name in, you can say, these quantitative techniques. He said that it is God's will, that the multicollinearity is always there. So if it is God's will, what we can do this, and you can say this is not a problem of OLS or any statistical technique in general. So according to this, I think you will be, and I will also be preferring this school of thought, because most of the time we are favoring the people who give us the shortcut. So this is cannot be totally ignored. I am not humiliating this concept, but I am saying that this gives a very insight to us that the multicollinearity is always present in the data. So if it is God wills, according to the Blanchard, we can't do nothing from this. What Blanchard is saying, that multicollinearity is essentially a data deficiency problem. That is not the problem of technique, but it is a problem of the data deficiency. We have, if this is the problem of data deficiency, then what is that? We have no choice over the data that is available for empirical analysis. If you are working on the secondary data, you go there and you see that in Economic Survey of Pakistan or in any of the publication, you see that there is the data deficiency, then you have no alternate. You have to use the same data. If it is only for 10 years, then you have to use this data for this. So according to this school of thought, then when there is problem of multicollinearity, do nothing, it is God's will, it is by default into the data, and the researcher has no control over the data. He or she will have to use the data in a similar way. Now this was the first school of thought. Now I am coming towards the other school of thoughts that say no, that there are some rule of thumb that we can apply this. According to them, that we may have some prior expectation, prior information. If we have some prior information, then we can reduce the problem of multicollinearity. For example, I am writing here that if Y is consumption and it is based on beta 1 plus beta 2 x2, that is our income, and beta 3 x3, that is wealth. So I will be mentioning here, this is wealth, this is x2 is income, and this is the Y, that is the consumption. Very simple example I am using. Everyone should know this, that the consumption is dependent upon the income and the other is the wealth. So what is this? If we have some prior information, for example, we say that the effect of wealth is 1/10 of the effect of income on the consumption behavior, then we can make some of the calculation here. I would like to repeat this. अगर हमें ये पता चल जाए कि इनकम भी इफेक्ट कर रही है वेरिएबल वाई को और जो है वेल्थ भी, बट द इफेक्ट ऑफ वेल्थ इज 1/10, कि अगर उसका इनकम का इफेक्ट कंजम्पशन पे 100 है तो इसका 1/10 0.10 पर जो है वो होना चाहिए, दैट इज इक्वल टू 10%. So I suppose that we have the prior information that this is the situation. So in this situation, what we will become, I would like this, that now you can see, now you can write that the beta 3 has become equal to 0.10 beta 2. Look at this here. This is beta 2. This is the effect of income on consumption on Y. And we are assuming that the beta 3, that is the effect of wealth, it is 1/10 than the beta 2. So what is this? Beta 3 is equal to 0.10. What is this? This is the effect of wealth. This is the effect of income. And this is 1/10 of this beta 2. So if I replace this back into the regression, so this will become Y plus beta 1 plus beta 2 x2 plus beta 3. Rather than writing beta 3, I can substitute this value. So I will be writing here 0.10 beta 2 x3. So now the model has a bit change. If I go further, it will become yi is equal to beta 1 plus I take the beta 2 as common, and it will become x2 plus 0.10 x3. Now if this is the situation, now I assume that this x2 plus x3 is equal to xi. Now my model will become yi is equal to beta 1 plus beta 2 xi. Now I can, if I run the regression and I found the value of beta 2. For example, the value of the beta 2 is equal to 0.6. Now it is beta 2 hat. The value of the estimated parameter is beta 2 hat. So what is this? I have just calculated the one parameter, but on the basis of my prior information, I can now immediately get the value of beta 3. If you go to this equation, that beta 3, now beta 3 hat is equal to 0.10 multiplied by beta 2. Rather than writing beta 2, I will write the value of beta 2 here. So this will become that the beta 3 hat will become, if you see this is 60 and 0.06. So this is the value of, if you see, this is 0.06. So this is the value of beta 3. So now in this way, when we will be estimating this, we omitted one of the variable, that was the x3. So what is this? We did not calculated the beta 3 separately, but on the basis of this, we calculated first beta 2 hat and then beta 3 hat. So what is this? We are saying that this is a way that if we have the prior information, we can do it a manipulation in such a way that it helps us to reduce the multicollinearity. So if you look at here, once we obtain the beta 2 hat value as we obtained here, if you can see, this is the beta 2 hat value, then you can say that we immediately can estimate it from beta 3. The prior information comes from previous empirical work. There is no sum of special formula that we come to know that there is prior information. It totally comes from the previous your knowledge, previous history, previous review of literature. The other rule of thumb procedure, the first was that you manipulate in such a situation on the basis of the prior information that ultimately you are able to reduce you can say you are able to reduce this one, multicollinearity. The second is combining cross-sectional and time series data. So as I said, this is called the pooling of data, or you can say the panel data, pooling of data. So what you are doing this, a variant of prior information. I suppose that you have no prior information, so you do not use this technique, that is the rule of thumb of prior information. But if you you are unable to find the prior information, it doesn't mean that now you are unable to detect the to make a remedy of the multicollinearity. You can make the remedy, and this is the most commonly used, and this is the very simple method that you pool up the data. And when you will be pooling up the data, there are chances that the multicollinearity will decrease. And you will be combining the cross-sectional and time series data. It is also known as the pooling of the data. So if I would like to say here, for example, if you have data of 1960 upward 2020 for, I say, the Pakistan, and if it is for 3 variable, that is, you can say the tax, the GDP, and I say the population. So if this data, if you find that there is multicollinearity in the variables, so you add some other cross-sectional unit. For example, you add India, and you can add Nepal also. Nepal, Sri Lanka, whatsoever. I am most of the time bothering about the countries that are in neighbor of the Pakistan. So if you pull up the data, cross-sectional and the time series, there are chances that the multicollinearity, if it is severe, it reduces up to the tolerance level. The third and very simple, and you can say the very simple, and you can say the awkward method to reduce the multicollinearity. What this says, simply drop a variable. If 2 variables are multicollinear, then drop one of the variable that you think that this is not much reliable as compared to the other, or you can say this is less reliable as comparison with the other variable. But at the same time, I will be explaining it later. At the same time, you will be coming out of the one problem to another problem, because you will be tapping into the specification bias. What is the specification bias? We assume that our model is correctly specified. If your variable is important, you have excluded it, and now you are falling into the specification bias. So to deal with severe multicollinearity, one of the simplest, I would say the awkward things to do is to drop one of the collinear variable. If the two variables, for example x2 and x3 there is high multicollinearity between these two variables, you can drop one of these variables. For example, in the previous example of consumption is dependent on income and wealth. If you take the correlation of income and wealth, for example, I say that I take the correlation coefficient between, now I means income and W mean wealth. So if it is 90%, there is high multicollinearity. It means we have detected. Now what is the solution? We have no prior information, and the other is we can't use the more data, that is the cross-sectional or the time series data. We say that this is the limited. So what is this? Most of the time, going back to cross-sectional data technique, that the researcher has limited data. So, and unfortunately, if you increase the data, the cost of data also increases. So the previous one, that is not easy as it looks very easy, that bring the data to this, but sometimes it is costly and it causes many of the problems. So I assume that income and wealth, so I am, you can say, dropping wealth. So if I drop the wealth from here, so what I have did, I have used the simplest way and I have dropped one of the variable. So as I dropped one of the variable, I can say that there is now specification bias. Why this is specification bias? Because now our model is misspecified. Our model is misspecified. So out of one problem, you are falling into the other problem. It similarly happens, for example, if a doctor gives a dose to a person, for example, say for the blood pressure, and the patient is also have the problem of, you can say, the sugar, then there is, you can say, this medicine may increase his sugar level, or you can say the blood pressure. So there is trade-off. Now particularly it happens in the people who have age more than 70. You will see that when the doctor is applying one medicine, he is able to control one of the disease, but at the other, on the other side, the other increases, the other disease may emerge. So this is the dropping the wealth variable would constitute the specification bias. Hence, now this is very interesting in sentence. Hence the remedy may be worse than the disease. इलाज जो है वो आपका बीमारी से भी खतरनाक हो गया, but it is in some situation. But if we see that the variable you have dropped is not of much importance, then you can say that there is not a specification bias. This was the third way to address the problem of multicollinearity. The rule of thumb, the fourth rule of thumb is that transformation of the variables. You transform the variable in such a position that reduces the problem of multicollinearity. For example, if I take that you have this kind of series yt is equal to beta 1 plus beta 2 x2 plus beta 3 x2t plus beta 3 x3t plus ut, I say. What I say that you take a previous value rather than the current value, you take the previous value, and I say that you write it yt minus 1 is equal to now beta 1 plus beta 2 the previous values of the variable x2 t2 minus 1 plus beta 3 x3 t minus 1 plus ut minus 1. This is the first equation. This is now the second equation. I have done nothing, but I have just taken the current value. I am taking the previous value. So what I did, now I subtract the second equation from the first. So if I subtract, this will become yt minus 1. The current value minus the previous value, it will equal to beta 1 minus beta 1 plus beta 2 x2 t minus beta 2 x2 t minus 1 plus beta 3 x3 t minus beta 3 this one x3 t minus 1 plus this one ut minus ut minus 1. Now further, if I go for this will cancel out, and this will become a simple that yt minus 1, and if I take beta 2 hat common from here, if I don't put hat on because we have not estimated yet them, so this will become beta 2 into x2t minus x2t minus 1 plus beta 3 x3t minus x3t minus 1 plus ut minus ut minus 1. I would write it that now it is vt, and you can say that vt is equal to ut minus 1. So if I say that this is the y star, now I have to bring it in estimation form. It will become beta 2 x2 star, and y star is equal to this one, x star, now x2 star is equal to this one, beta 3 x3 t star, this is x3 star, and this is equal to this one, and this is plus vt. Now we have transformed the variables. Rather than taking the current values, we have done some mechanism here. So what we will say that when we transform this variable, this is called, this approach that I have used here, that is called the first difference approach. If you remember, you can see here we have done the same thing there. And the model often reduces the severity of the multicollinearity. If you transform your model in such a way, it reduces the severity or severeness of, you can say, the multicollinearity. But again, getting out of one problem, you are falling into the other problem. So what is now the problem? That now this is the VT. Now it is also based on the assumption. We are making some assumption about the VT that this is random. It is not necessarily that it is fulfilling the assumption. So from one problem, you are again going to the other problem. So again the remedy may be worse than the disease. आप चले थे जो है वो नमाजें बख्शवाने, आपके रोजे भी जो है वो गले पड़ गए. So this is the situation here, that you try to get rid of one problem, the other problem immediately arose there. So this was this. So ultimately we will be finding that how to overcome this problem, that how when we are getting out of one problem we are falling into other problems, then there is what to do in this situation. This was the first technique, method of transforming the variable, and this is called the first difference transformation. Now there is another technique that is called the ratio transformation. If we see that the variables are multicollinear, so we can transform into some another kind that is the ratio, that is called the ratio transformation. Look at here. For example, I say that in Pakistan, taxes depend on GDP plus you can say the population, and I can other say that this also depends on the, you can say, the government expenditure, GE. Now the government expenditure, I say that this is the GE. Now I suppose that the GDP and GE, that is the government expenditure, these are multicollinear, I suppose, and in reality these are multicollinear, because as the GDP increases, the revenue, the government expenditure also increases. So if this is the situation, now rather than transforming into the first difference, I want to make in such a position that the multicollinearity reduces, and I am using the ratio transformation. What ratio transformation? I will show this everything in per capita term. Per capita term means that I will divide all the terms by total population. This is total population also, and this is the government expenditure. Now the model will becomes taxes over population is equal to GDP over population plus population over population, total population over total population, plus government expenditure over population. So now you have transformed your variable into using the ratio technique. So what is this? It will also reduce the severity of the multicollinearity. So these were two techniques that how you transform the, your variable to get rid of the severe multicollinearity. The other rule of thumb that is very easy, that is additional or new data. Bring more data, because the multicollinearity is the problem of sample, and as the sample increases, I repeatedly said that many of the problem of multicollinearity, many of the problem are solved, and this problem is also solved. But what is this? Sometime increasing the size of the sample may soften the collinearity problem. ये आपका कोलिनियरिटी का प्रॉब्लम को काफ़ी सीवियर है तो सॉफ्ट कर देगा. बट अनफॉर्चुनेटली इकोनॉमिस्ट seldom can obtain additional data. Now not only the economist, why they have used the word economist here? Because economist has every time on eye on the cost and benefit analysis of the issue. So as you will increase the observation, and it will go to infinity, cost will also increase, and I can say it may go to infinity. So this is a very easy rule of thumb, but at the same time the problem with it is that sometimes the new data is not available, and sometimes the data is available but it is much costly. So now it is up to you which kind of this you use. The next rule of thumb is that reducing collinearity in the polynomial regression. If you remember that some of our models are linked in such a situation that there is a quadratic term also, and then there is you can say the polynomial term is also there. For example, if I would like to this that in our cost analysis we put, for example, this is the cost, and it is a function of beta 1 plus q1, beta 2 q plus beta 3 q square plus beta 4 q3. Now we have added, if you see that the cost is not influenced by output, but it is also influenced by the square of output and also by the cubic of this output, that is now the polynomial situation. There are many power of the, you can say, the independent variable. So one practice, if this is the situation, one practice is that if variable are expressed in the deviation form, if I express these variable, that is the q that is the q square, and this is the q, and if these are the q minus q bar from deviation form, then it can reduce the problem of severity. Rather than using the simple, I can use the deviation from mean for the variable, and it may reduce the problem of multicollinearity. But even if the problem is persist, if you see that you applied this, that you mentioned your variable rather than in absolute term used in the model in the, you can say, the deviation from the mean, but still you found that there is problem of multicollinearity still exists, you can go for another method that is beyond our discussion, but you should remember its name, that this is the orthogonal polynomials techniques. So if this is the situation, you can go for this. The last rule of thumb that we are studying here, that there are some other methods that can explain this situation, that can help us in reducing the multicollinearity. What is the other techniques? These are called the factor analysis. I am not going to explain any one of these because there are many techniques, and if we run after every techniques, it is difficult for us to complete our course. The other, this is the factor analysis. The other is principal component technique, and there is also a technique that is called the ridge regression. These are often employed to solve the problem of multicollinearity. So we studied the 7 methods that can reduce the problem of the multicollinearity. Now here is some of the concluding remark. Is multicollinearity necessary or bad? Maybe. The answer is maybe, not if the objective is prediction only. If we are only interested to predict the values, then this is not a big problem, because we will not be testing our the t statistics of our variable. So in general, it is not a serious issue, particularly in large sample. This is issue in small sample, but in the large sample, this is not a big issue. So I would like to give you summary of today's lecture, because now we have completed our discussion about the multicollinearity, and from the next lecture we will be selecting another problem of regression, and we will be talking comprehensively on this. So what is the, you can say, the summary of today's lecture? We started from how to detect the multicollinearity. What was the multicollinearity? We discussed in the more previous lecture. So what we started, that there is how to detect the multicollinearity, and in this lecture we started from the auxiliary regression. Auxiliary regression, the mechanism is there, I am not going to explain, but at the end you will be comparing your F calculated with your F tabulated. If your F calculated is greater than the critical F, that is the tabulated F, then you will reject the null hypothesis, and your null hypothesis was that there is no multicollinearity. So if you will reject this, immediately you will come to know that there is a problem of multicollinearity. After detecting this one, we went further for the variance inflating factor, and the other was the tolerance factor. So variance inflating factor means that this is the factor that increases the variance. So if the value of the variance is higher, VIF, now the variance inflation factor, if its value is higher, we say that there is a problem of multicollinearity. And what this means, as the value of the variance inflation factor exceeds the value 10, it becomes severe. And interestingly, it is a link with the R square, that is the coefficient of determination. In the tolerance factor, we said that it is equal to 1 over VIF. As the VIF increases, the value of tolerance is the tolerance index goes to 0. So what this means, that as the tolerance effect goes to the 0, there is severe multicollinearity. Now there was another technique that we used in detecting the multicollinearity, that was the K-index. K-index is based on the maximum and the minimum eigenvalues. You will be worried about from where you will get these eigenvalues. Eigenvalues are reported by many of the statistical packages, and if there are it doesn't report these values, then you will have to use some other technique to get the eigenvalues. So there is K is equal to maximum eigenvalue divided by the minimum eigenvalue. So if you will come with definitely a value of the K, and the value of K will enable you to whether see that there is multicollinearity or not. The range of now the interval is between 100 and 1000. If your calculated value, that is now the K, is converging towards 1000, it means you are going towards the upper bound of the class, the interval. And if you are going towards the upper interval, it means that there is severe multicollinearity. And if this K index even goes beyond this level, then there is very, very severe multicollinearity. And if you come to the other factor, that was the, you can say, the condition index, it was nothing but it was only the square root of the K. So as you take the square root of the K, its range becomes, you can say, narrow. And now the range is between 10 to 30. So 10 to 30 means now if you get the values of Ci, that is now the condition index, you will be seeing that there is, if the value is between 10 to 30, there is high multicollinearity. The more you are near towards the 30, the more multicollinearity there. But if it goes beyond these limits, then there is severe multicollinearity. Then we studied that what is the remedial measure for this. These were the very interesting, because we want to get rid of this. And before telling that what were the remedial measure, I would like to explain that it is the possibility that we are solving the problem of multicollinearity, we are falling into another problem. So the first detection method was that we have some of the prior information. On the basis of this prior information, we manipulate our model in such a way that we get rid of this multicollinearity. The other was, the simple was that drop one of the variable. Very simplest way, that but at the same time as we drop one of the variable that are collinear with the other, we face the problem of the specification bias. The other was that we should pool the data. If we are working only on time series data and we have cross-sectional data, we should pool this, and so that we can get the pooling of the data is also has potential to reduce the problem of multicollinearity. Another technique that we confront in detection the multicollinearity, that we transform the variable. In this situation, we studied the two approaches, the first difference approach and the other was the ratio approach. In first difference approach, we manipulate our model, and ultimately we suppose that it is not necessary that if the current values are correlated, it is not necessary that the previous values will be correlated. Then there was the ratio transformation technique, and ratio transformation technique was that in which we try to divide every of the term of every variable with some of the other variable. In our example, this was the population, where we showed that taxes, GDP and government expenditure, we showed them as a percentage of, as per capita, tax and expenditure per capita, GDP per capita, government expenditure. And at the before detecting this, we also confront with one school of thought, that was do nothing. That was led by the Blanchard. According to the Blanchard, the crux and the, you can say, the core of this discussion of do nothing approach is that the multicollinearity is God's will. So if it is God's will, it is there in the data, so you should not do this. You should not criticize your estimation techniques, because this is the multicollinearity is not due to your OLS estimator, it is due to the you can say the data collection methodology. The other was, at the end we concluded that is this the multicollinearity every time bad? Yes, if it is severe, this is bad, but if it is up to tolerance level, what this means, the up to the tolerance level, that it is less than 80%, so we can tolerate it, and it is always there. We are not worried about whether it is present and whether it is not present. We are worried about its degree. And interestingly, as the sample size becomes larger, then there is this problem of multicollinearity is solved automatically. So this is the discussion on the multicollinearity topic. I have concluded this. So goodbye and Allah Hafiz.